Welcome to the Explainer. You know, when we look at a massive city skyline, we're really only seeing half the story. Today, we're going deep underground. We're going to uncover the invisible, completely hostile environment right beneath our feet and look at the intense physics required to keep our massive structures safely anchored. So, before we dig into the really technical details, just ask yourself, how do engineers actually conquer the unpredictable Earth to support literally thousands of tons of steel and glass? I mean, you might think you just dig a big hole and pour some concrete, right? But the Earth is this living, shifting thing. It's got groundwater, crazy variations in soil density, and just immense pressures. Supporting a megastructure down there requires an absolute mastery of both physics and geology. All right, here's our roadmap for today. We'll start with the secrets of deep foundations, then look at the magic of mini piles, move on to the physics of pile driving, and finally wrap up with beating underground engineering challenges. Let's get into it.
Okay, Section 1, Secrets of Deep Foundations. Let's talk about reaching bedrock.
To really understand how these massive, heavy loads are transferred deep into the Earth, we have to look at something called the rock socket. Now, a rock socket is essentially the ultimate anchor. It's drilled directly into solid rock to resist forces pushing down, pushing sideways, and, get this, even forces pulling up. But there's a really fascinating quirk of physics here. Because of something known as the negative Poisson ratio, we can actually only rely on about 70% of its uplift capacity. Why? Well, when tension pulls the socket upward, the material naturally wants to contract, or kind of thin out slightly, and that actually reduces its friction against the surrounding rock walls. Now, what's really interesting is the exact step-by-step load transfer mechanism of a rock socket. It isn't just a static column sitting there. At first, with really small movements, it behaves elastically. But as the immense weight of a building presses down, that bond between the rock and the socket actually begins to fail. The friction strength drops down to a residual value, and then those massive loads are transferred entirely down to the very base or the socket end. So it's actually a very dynamic, shifting transfer of energy.
You might be wondering, with all that crazy weight, do these concrete pillars ever just buckle or snap underground? Well, surprisingly, no. The surrounding soil usually holds them incredibly tight. Piles rarely shear or buckle under normal conditions. But as experts like J.P. Tyson remind us, we still absolutely need nominal reinforcement to fight back against the violent lateral forces of earthquakes. The Earth might hold the piles steady normally, but when the Earth itself shakes, that reinforcement becomes the building's literal lifeline. Moving right along to Section 2, the magic of mini piles. Let's look at some really smart space solutions. So, what happens when engineers are severely limited by headroom or space? They turn to the mini pile. Because these piles are so incredibly slender, we're talking sometimes a diameter 100 times smaller than their length, they need special protection. By intentionally leaving the steel casing in the ground, engineers basically create an armor. This left-in casing fights off corrosion. It provides restraint against lateral buckling, stops groundwater from just ruining the concrete, and prevents the concrete from thinning out, which is called necking, during the lifting phase. It's a real lifesaver for the structure. And to expand the pile and really grip the surrounding earth, engineers use this purely ingenious post-grouting technique. It acts almost like structural acupuncture. So after the initial pile is set, engineers pump highly pressurized grouts straight down a tube. This immense pressure physically ruptures the initial hardened grout, forcing the new mixture to bleed out and interlock with the surrounding soil zones. It effectively increases the diameter of the pile underground, and that massively enhances the skin friction that's actually holding the building up. Okay, Section 3, the physics of pile driving. This is all about raw, violent, kinetic energy. When it's time to bring in the heavy machinery, building codes actually demand a hammer-to-pile weight ratio of greater than 0.5. Why is that absolutely crucial? Well, if you try to drive a massive steel pile with a hammer that's too light, you get terribly inefficient energy transfer. I mean, think of hitting a giant steel railroad spike with a tiny little tack hammer. Instead of moving the pile, the energy just bounces right back, creating damaging tension inside the hammer itself. You really need comparable masses for an efficient collision. To make sure a pile is driven perfectly, engineers use something called High-Lee's formula. But when using this formula, we have to precisely calculate two major areas of energy loss. First up is hammer efficiency. This is the kinetic energy lost swinging the hammer, stuff like guiding friction or misalignment before the hammer even makes contact. The second is the coefficient of restitution, which is the energy lost during the actual physical collision.
If that collision isn't perfectly elastic, energy is just lost to heat and deformation instead of doing what we want, which is driving the pile downward.
Because these forces are so extreme, you can't just go and smash a raw steel hammer directly onto concrete or steel. It would be a disaster. Instead, engineers layer specific tools between the hammer and the pile. The cap lock compresses elastically to lengthen the blow time. The drive cap uniformly distributes all that intense energy, and the pile cushion acts as a literal shock absorber to prevent the top of the pile from just instantly shattering under the immense stress of those hammer blows.
But hey, what happens when the final resting place for the top of the pile is underwater or far below the current ground level? Well, we use clever tools called followers. A follower is basically a temporary extension. It transfers the blow from the hammer down to the pile head. This lets us drive H-piles super deep beneath the surface without having to leave expensive, wasted steel just sticking out of the ground only to be cut off and thrown away later. It's a really elegant solution.
Finally, Section 4, Beating Underground Engineering Challenges. Let's look at some hostile obstacles. Geology rarely cooperates, right? And the deeper you go, the tougher it gets. When drilling these massive boreholes, the surrounding earth constantly wants to cave in on itself. So to keep a deep hole from collapsing, engineers have to carefully circulate drilling fluids, choosing between two opposite flow directions based on the soil conditions. Direct circulation pushes fluid down the drill stem to flush cuttings up the outside. Reverse circulation does the exact opposite. And this fluid doesn't just cool the drill down, it physically holds the walls of the hole open through pure hydrostatic pressure. Pretty wild, right?
Another massive challenge is accurately predicting how the soil will react to a building's movement. As engineer Brian Leach demonstrated back in 1980, you can't just guess soil resistance. Assuming a constant modulus of reaction across all depths is a really dangerous mistake. It overestimates the maximum reaction force and vastly underestimates the bending moment the pile will experience. So engineers actually have to conduct pressure meter tests right inside the boreholes to understand exactly how the soil behaves at different depths. No guesswork allowed. Now here's one of the most counterintuitive challenges: negative skin friction. Normally, friction from the soil holds a pile up. But if the surrounding soil is settling, or say a water table drops, imagine the surrounding soil actually dragging the pile downward. That's negative skin friction, and it adds a massive unwanted load to the foundation. Engineers defeat this by actively making the piles slippery. They'll use bitumen coatings, opt for thinner pile designs like H-piles to reduce the surface area, or just design the pile to rely entirely on the hard bedrock at the bottom, totally ignoring friction altogether. To ensure absolute safety, these piles are rigorously load-tested before a building even goes up. Engineers apply massive test weights to map out exactly how the pile behaves under stress. When the test load is removed, the pile bounces back, but not perfectly. By measuring the permanent settlement versus the temporary elastic movement, engineers can confirm exactly where the true center of resistance is, deep underground. You know, understanding all these underground solutions really makes you look at the skyline differently. Every towering skyscraper is balancing on an invisible network of highly engineered giant concrete roots, gripping the earth, fighting off seismic waves, groundwater, and immense pressure. It really leaves us to wonder, as our ambitions reach higher and higher into the clouds, how will foundation engineering have to evolve to safely support the megastructures of tomorrow? Thank you for joining me on this explainer, and keep your curiosity grounded.